I'm going to start with a very exciting experiment. Here in Canada, Ontario, there's a company called Xanadu that they use photons to make quantum computers. And in 2022, they did an experiment that demonstrated that they can solve a problem that takes the fastest supercomputer on our planet 9,000 years. They were able to solve this problem in less than a second. They solved this problem in 36 microseconds. So just think about that. How much energy a supercomputer much bigger than this place takes compared to a photonic-based quantum computer that is slightly bigger as one of your lunch tables plus some electronics. And perhaps that's why we are here. That's why we are so interested in quantum, because we know they have so much potential. By the way, this was not the only experiment that demonstrated such a huge advantage over supercomputers, classical supercomputers. A couple of years before that, a team of scientists at Google and University of Santa Barbara demonstrated something similar. Scientists in China demonstrated something similar. And 2 years after that, a Canadian-based company here in BC demonstrated similar shocking results. Now, the question is how quantum computers are able to demonstrate such great computational power. The other question is, if they are so powerful, why we are not using them, why we don't see them in our everyday applications. And one of the questions I got among the conversations with you is that where are they, how we can use them? A lot of people think these quantum computers are not really accessible. So I'm going to start first with answering that. You can access these quantum computers, this one in particular, the one that we have in BC called D-Wave. There are some in New York by IBM. You can access it right now on your laptop. You can open your laptop, go to the IBM website, go to the Xanadu website, go to the D-Wave website, open an account, and use your Python coding to get access to these computers. Don't get me wrong, if you know Python and have a laptop, doesn't mean that you can just start using a quantum computer right now. You may need some training, but what I'm saying is that they are pretty accessible these days. Now, in the rest of the conversation, we are going to understand why they're so powerful and what are the applications, why we don't see the applications in our daily basis use cases. So first of all, I want to clarify that sometimes we think quantum computing is something new. Using quantum for applications is something new. How many of you use quantum on a daily basis? Have you ever used a device that uses quantum mechanics? So this computer, this clicker that I'm using, your laptop, your phones, without quantum mechanics, they're not going to work. All the components in them, the transistors, the lasers, even solar cells use quantum mechanical principles like quantum tunneling, quantization of energy levels. Quantum mechanics have been around for more than 100 years, and it's more than 50 years that we are using them in different applications. MRI, for example, is another well-known application of quantum mechanics. But what really differentiates what we recently hear about quantum, basically quantum computation, is a new wave or a new revolution in using quantum mechanics for applications such as quantum computing. And why quantum computing is so revolutionary? Do you know how your classical computers work? Like if you break down the code, the system, what is the most fundamental piece of information in a classical computer? What is the data made of? Bits, zeros and ones. So classical computers use transistors that may use quantum mechanics in their process of building them, but the data is purely classical. It's zeros and ones, as simple as it gets. Quantum computers, however, use something more quantum, more advanced. And they use a principle called superposition, which means that the data is in a probability of 0 and 1. And in order to accurately represent that, we use this ball of information. Basically, the state of your information in quantum computing is somewhere in this ball. And we use an arrow somewhere in this mathematical model to represent the state of our qubit. And because of this fundamental difference in the way that we represent information and in the way that we make our hardware, we are able to come up with completely new algorithms and a completely new way of computation. On another level, the hardware of quantum computers are also fundamentally different from classical computers. What is the basic component of every computer or laptop or phone that you use, regardless of the brand? The smallest building block of computers. Transistors, correct. All the computers, regardless of what brand you use, they use transistors, and almost 98% of these transistors are made with silicon. In the quantum computing world, there are a variety of ways to make quantum computers. The field has not matured enough to choose a specific hardware. Different researchers, different organizations, different companies use different technologies. For example, one of the most well-known technologies for making quantum computers is using superconductors or superconducting qubits. These materials operate at very low temperatures, lower temperature than outer space. We are talking about close to 0 Kelvin, several millikelvins. And because of the complexity of getting to low temperatures, if you have seen a picture of a quantum computer, I'm going to show it to you here. You can see one on the right side. They have this massive, some people call it chandelier or fridge, to bring the temperature down. But at the end of the day, the superconducting chip is a very small piece of chip at the bottom of this big system. So I want to make sure that we all know quantum computing hardware is fundamentally different with classical computing, and there is not just one type. These are just some examples. Some of them use ions, some of them use silicon. There are other types that use lasers to read and write the data, and then some of them use superconductors. So when you hear in the news about a company making quantum computers, check what type of hardware they use. If you want to invest in one of these technologies, check what type of hardware they use. And there are different metrics to assess the capability of computers based on their hardware. Now, we talked about the information at a high level. We know the information in quantum computation is fundamentally different from classical computer. And at the lower level, we understand the hardware is also completely different. We don't use transistor anymore. But if we go a level higher, if you call it architecture or model, there are also different models for using quantum for computation. The most well-known model or universal model is gate-based model quantum computing. And basically, you have these gates, these blocks. Anybody from electrical engineering background? Yeah, a lot of people. You remember AND gates, OR gates? Okay, in quantum computing, we don't have them anymore. We can say goodbye to them. We have different gates here. We have quantum gates, and they work. This superposition we talked about, one of the gates is superposition. We have protocols to apply entanglement. So all these philosophical quantum concepts are being really used here. So gate-based model, keep that in mind, or universal quantum computing. And companies like IBM, Google, Rigetti, Xanadu, most of the companies in quantum computing use this because it's very versatile. It can solve a variety of problems. Now, there's another theory to use quantum mechanics for computation. It's called quantum annealing or Ising model. Have anybody heard of that model before? Oh, this guy is the expert. Like, he's doing it for more than 20 years. Okay, this is a very exciting model for using quantum computation. And the most exciting part of it, at least in my opinion, is that how early we started using this model. Here in BC, Canada, we have a company called D-Wave that they had the courage. I was listening to the mayor of Whistler about their ambition, and this company was very ambitious. They started using quantum mechanics to make computers back in 1999, 2000. At that time, there was no commercial quantum computing. So we have Maury from D-Wave, who has been probably one of the first employees, right? Yeah, 22 years he has been working there. So they use a completely different way of using quantum mechanics for computation. And I was talking with someone who asked me, can I use quantum computers to find the lowest cost for my problems or lowest energy level? And we were talking about this model is very good for optimization. And they have a vast library of examples that they have helped a lot of industries and companies to solve their optimization problems. So if you are interested in optimization, talk to Maury. Now, I talked about this fascinating experiment, a problem that takes 9,000 years solved in 1 second. Well, then if the quantum computing is so powerful, why we are not using it for everything? Well, the truth is that examples like that are very, very limited. We have only a handful of examples that a quantum computer can be faster than any classical computer on Earth. And you have to keep in mind that those examples are very specific research-based examples. They are not like the latest machine learning problem. They're not a problem that you may use on an everyday basis. So they are basically demo problems that are used to demonstrate the power of quantum computing. So because of the fact that quantum computers use these qubits, as we increase their capacity, their capability increases not linearly, but much faster than linear. How much faster depends on many things. They're kind of sensitive to noise, so depending on what kind of error correction you use, the capability of quantum computers can grow really fast. But what I want to point out from this figure is that because of this recent experiment, we have passed this critical point. So we have enough data that we know quantum computers can be faster than any classical computer. But if we really want to get to a point that quantum computer can show really competitive advantage with the fastest classical supercomputers, we need better hardware. And depending on who you ask, some companies believe that we are 2 to 3 years away from that. Some scientists believe that we are 7 to 10 years away from that. But what you should know is that quantum computers are available right now. And probably a lot of problems in your organization that you have right now, there might be possibly a solution that quantum computer can give you a better result. Of course, if you hire scientists, they might be able to find a better solution using a super fast supercomputer. But we are at the stage that you can run exciting problems on quantum computers. And we know in the near future, they are going to be unbeatable in certain problems. Somebody asked me, are they going to replace classical computers? Not as far as we know. It's predicted that quantum computers will be used in parallel with classical computers because they are good at certain problems. And even right now, if you use a quantum computer, it is possible that a classical computer behind the scenes is reformulating your problem so the quantum computer can solve it more effectively. So we talked about how quantum computers data work. We talked about the hardware. And I hope you can understand how far we are in terms of development of this technology. We have achieved a lot, but there's a lot more exciting news that we are waiting for. What are the opportunities in quantum? I think that's what probably matters for you the most. Opportunities in quantum can be divided in different sections. One of them is simulation. Quantum computers are, for example, really good at solving chemistry problems because chemical compounds are by nature quantum, and quantum computers are also by nature compound. So mapping a small molecule on a quantum computer requires less simplification than classical computer. They are also really good at optimization. We use this example of quantum annealing. They're very good for optimizing, finding the fastest route, lowest energy level, the best scenario for finding the lowest cost of a problem. And there's a vast library of examples you can find in different quantum computing companies that show you where they are being used. Another example that might be very interesting for you is AI. There are a lot of research and applications in AI that quantum computers are being used. And probably for your sector, this must be very important because as I hear from you, it is expected that the databases that are being used for AI are going to consume a lot of our energy. And some people argue that it is possible that quantum computer can help reduce the load of our energy by solving some of these problems more effectively. This is something that I hope we can talk more in the roundtable. There are lots of interesting opportunities and opinions. Finally, there is also opportunity and risk about cybersecurity and cryptography. How many of you have a cybersecurity department in your organization or use secure data in your organization? Okay, so let's talk about that a little bit because there's an algorithm that was basically invented by a brilliant scientist called Peter Shor in 1995. At that time, there was no quantum computer. I don't know how he came up with this idea. But he invented this algorithm that can that can do factoring problems very effectively. And a lot of cybersecurity or cryptography protocols use factoring. So RSA is, for example, a well-known cryptographic model. And these quantum algorithms are very good at breaking RSA. We already know that. So they can easily break into your RSA. That's bad news, right? But the good news is that the quantum computers are not powerful enough to run Shor's algorithm to the extent that can break your RSA. So you are safe for now. But there's a bad news. There are some people who are storing your data right now so they can decrypt it later. And there's another bad news based on a survey done by 37 experts in quantum, done by a company called EvolutionQ in Canada, a fantastic quantum cybersecurity company. The majority of these people believe that there's a 5% chance that in 5 years, quantum computers will be powerful enough to break into your cybersecurity. So for those of you who have a cybersecurity department, do you think your company can tolerate a 5% of chance of data leakage? Maybe yes, maybe no. So keep that in mind. And as the timeline grows, the chance of quantum computer being able to break into your systems gets higher. I want to end the presentation before we get to the roundtable and talk specifically about applications that are more connected to your field. I'm going to end with a sort of activity or a use case of quantum computers. There's a problem called traveling salesperson, and I heard a lot of people travel to multiple locations to get here. You can solve this problem with a quantum computer easily on your phone right now. So if you scan this QR code, it will take you to a website that we built at UBC, and you can either choose locations in Vancouver or North America. And what it does is that it finds you the optimum path for you to go through multiple locations. And it connects to one of the quantum computers here in BC, solves the problem, and give it back to you. So the idea is that you know how accessible quantum computers are. I hope you enjoyed the activity, and I hope you learned something from it. Thank you.